Many-valued logic is a family of non-classical logical systems that postulates more than two truth values. Usually, systems in this family reject the assumption that every meaningful sentence must be either true or false, or that no sentence can be both true and false. In classical logic, each well-formed sentence has exactly one of two truth values, true or false. Many-valued logic challenges this assumption by allowing more than two truth values. Depending on the system, sentences may take 3, 4, or even infinitely many truth values. These logics provide formal tools for reasoning in contexts where classical assumptions seem inadequate or overly restrictive. The motivation for many-valued logic comes from several philosophical, logical, and practical considerations. Some philosophers have argued that there are sentences that are neither true nor false, for example, statements about future contingents, vague predicates, or fictional entities. Others have claimed that there may be sentences that are both true and false, as in certain paradoxical cases involving self-reference. Many-valued logic offers a framework in which such intuitions can be formally represented and explored. One reason for developing many-valued logic is dissatisfaction with classical logic's treatment of vagueness. Consider a statement such as, "This heap is tall." In borderline cases, it may seem inappropriate to classify the statement as simply true or false. A many-valued logic can introduce intermediate truth values, such as indeterminate or partly true, to better reflect our intuitions. Another motivation arises from paradoxes such as the liar paradox. This sentence is false. Some logicians have argued that such sentences are neither true nor false, while others have suggested that they are both true and false. Many-valued logics, including paraconsistent and paracomplete systems, allow us to model these possibilities without trivializing the logic. In addition, many-valued logic has applications in computer science, artificial intelligence, linguistics, and decision theory, where reasoning often involves uncertainty, inconsistency, or incomplete information. The central difference between many-valued logic and classical logic lies in the set of truth values and the interpretation of logical connectives. Classical logic uses exactly two truth values, often denoted 1, true, and 0, false. Many-valued logic extends this set. In a 3-valued logic, for example, there might be an additional value, for instance 1/2, representing indeterminacy. In a 4-valued logic, truth values might represent combinations of truth and falsity, such as true only, false only, both true and false, and neither true nor false. There are also infinitely many-valued logics where truth values range over a continuum, often interpreted numerically. As a result, some classical logical principles may fail in many-valued systems. For example, the law of excluded middle or the law of non-contradiction may not hold universally. However, many-valued logics are not arbitrary. They are governed by precise formal rules that determine how truth values are assigned and how valid reasoning proceeds. The syntax of many-valued propositional logic is usually very similar to that of classical propositional logic. It includes propositional variables, logical connectives such as negation, conjunction, disjunction, and implication, and parentheses to structure formulas. From a purely syntactic point of view, many-valued logics often look identical to classical logic. The difference lies not in how formulas are formed, but in how they are interpreted. This means that many-valued logic can be seen as a reinterpretation of familiar logical languages rather than a complete overhaul of logical syntax. As in classical logic, more complex systems can extend the basic syntax with quantifiers, modal operators, or other expressive devices. The semantics of many-valued logic generalizes classical truth-value semantics. Instead of assigning each sentence one of two truth values, an interpretation assigns each sentence a value from a set of truth values with more than two members. Among these truth values, some are typically designated as acceptable or truth-like, while others are not. Logical connectives are interpreted using truth tables or truth functions that specify how the truth value of a compound sentence depends on the truth values of its components. In 3-valued systems, 4-valued systems, and beyond, these truth tables generalize classical ones but need not preserve all classical properties. Logical consequence is defined in terms of preservation of designated truth values across all interpretations. As we have already mentioned, there are many different many-valued logical systems, for example, 3-valued logics, 4-valued logics, and infinitely many-valued logics. These systems differ in their philosophical motivations, their semantic structures, and the logical principles they validate. Some are paracomplete, rejecting the principle that every sentence is either true or false, while others are paraconsistent, rejecting the principle that contradictions lead to triviality. Several proof methods are used in many-valued logic. Truth tables can be generalized to handle multiple truth values, although they quickly become large and complex. Axiomatic systems provide sets of logical axioms and inference rules tailored to specific, many-valued logics. Sequent calculi and natural deduction systems have also been adapted to many-valued settings. In addition, semantic tableau and algebraic methods are often used to study many-valued logics. Each method highlights different aspects of logical reasoning and provides different tools for proving validity, consistency, and completeness. Many-valued propositional logics can be extended with additional expressive resources. Predicate versions introduce quantifiers and domains of discourse. Modal, many-valued logics combine many-valued semantics with necessity and possibility. These extensions allow many-valued logic to be applied to a wide range of philosophical and technical problems. In many-valued logic, a sentence is logically true if and only if it takes a designated truth value in every interpretation, logically false if and only if it never takes a designated value, and logically contingent if and only if it does so in some interpretations but not others. Logical consequence is defined as designated value preservation, and an argument is valid if and only if no interpretation assigns designated values to all premises while failing to do so for the conclusion. Many-valued logical systems vary widely in their metalogical properties. Some are sound and complete with respect to their intended semantics, while others are not. Decidability and complexity depend on the number of truth values and the expressive power of the language. In general, increasing expressive power tends to increase logical complexity. Many-valued logic provides a flexible and powerful alternative to classical logic. By allowing more than 2 truth values, it offers new ways of understanding vagueness, inconsistency, and indeterminacy. While it is controversial and departs from classical assumptions, it remains a rigorous and systematic approach to logical reasoning, with interesting philosophical and practical applications.